Hello, everyone. So last time we looked at the concept of limits at infinity. So we defined basically, limit f of x as x approaches to infinity equals L, and limit f of x as x approaches to minus infinity equals L. And we call them end behavior of a function. So end behavior means limit at infinity and or limit at minus infinity. And the definitions we provided were informal definitions, by the way. The formal definition of limit is given normally in sometimes in some honor calculus course, but most of the time in the basic analysis course. So you can take, for example, Math 225 or Analysis 1 to learn about formal definition of limits with epsilon delta definition, in other words. So these are the informal definitions we provided. So we also said that, so we saw that y equals L is a horizontal asymptote of f of x if at least one of the two conditions above holds. So these two conditions, if both of them or at least one of them holds, then we call y equals L a horizontal asymptote of f of x, and the abbreviation is capital H, capital A, stands for horizontal asymptote. Okay, so we also saw about how to compute the limits at infinity. So to compute the limits at infinity, we said that, if you have a polynomial, you can factorize the highest power of x out. And if you have a rational function, meaning a polynomial over another polynomial, still you can factorize the higher power of x out from top and bottom, and then simplify to calculate the limits. We also set some limit rules, which forms are determinate and which forms are indeterminate. So we also saw that 0 over 0. So 0 over 0 is one of the most famous indeterminate forms. Another one is infinity over infinity. Another one is infinity minus infinity. Another one is 0 times infinity. So these are indeterminate forms. And we need to simplify to compute the limits. And we also saw, okay, so when we say indeterminate form, means the answer potentially could be anything, could be 0, could be infinity, could be 5, could be 10, could be -2, depends on the example. Now, which one is the case? But we have to simplify. What do we mean by simplifying? Well, that depends on the type of function. If, for example, a square root is involved, we have to rationalize. Polynomials. For polynomials, well, depends. If we have 0 over 0, we have to factorize. But if it's infinity over infinity, we have to factorize from the highest power of x out, right? So polynomials depends on whether we have 0 over 0 or infinity over infinity. Or trigonometric functions, if trigonometric functions are involved, normally we have to connect it with limit sine x over x as x approaches to 0 equals 1. Okay, so the type of simplification depends on the type of indeterminate form and the type of the function. But some forms are determinate, meaning that, we can immediately write down the answer. For example, let's say infinity plus infinity is equal to infinity, or infinity times infinity is equal to infinity. Or let's say a constant over infinity is 0. Or let's say a non-zero constant over non-zero constant in the top over 0, then the answer is infinity or minus infinity. Again, depends on whether infinity or minus infinity. Depends on the constant and depends on whether it's 0 plus or 0 minus. So these are the things we saw last time. So let's look at some more examples. Find, let's say, limit square root of 3x squared minus x over 4x plus 1 as x goes to infinity, and limit root, again, 3x squared minus x divided by 4x plus 1 as x goes to minus infinity, and find the horizontal asymptotes of square root of 3x squared minus x over 4x plus 1. Okay, so now for the first limit, how can we calculate it? We have to factorize our highest power of x out. So what are we going to have? So limit root 3x squared minus x divided by 4x plus 1, x goes to infinity. So this one can take x squared out, then 3 minus 1 over x will be left. And here we can take x out. In the bottom, highest power of x is x, so x out, and 4 plus 1 over x is left. And then we calculate this limit. And then this will be limit x, because square root of x squared. Well, what is square root of x squared? That's one of the most common mistakes in all math courses. Square root of x squared is absolute value x. So this is limit absolute value x times square root of 3 minus 1 over x divided by x over 4 plus 1 over x as x goes to infinity. And then we will have, now, x goes to infinity, right? So x goes to infinity means it's positive. Infinity means, like, it will be 10, then 100, 1000, and so on. So it will be positive. So I can say that absolute value x is equal to x because x is positive. So then we'll have limit x times square root of 3 minus 1 over x divided by x over 4 plus 1 over x. Now I can cancel x with x, the top and bottom. And then I'll have square root, what will be the answer? Square root of 3 minus 0, right? So as x goes to infinity, 1 over x will be 1 over infinity, which is 0. Remember, any constant over infinity, it's 0. So 3 minus 0, root 3 minus 0 divided by 4 plus 0. And the answer is root 3 over 4. So this is the limit as x goes to infinity, and the limit as x goes to minus infinity. We can use a similar technique. So 3x squared minus x divided by 4x plus 1 as x goes to minus infinity. So this will be limit. So let's take x squared out again, 3 minus 1 over x. So it's very similar, only one step will be different. X goes to minus infinity. And then this will be limit, again, absolute value x times square root of 3 minus 1 over x times 4 plus 1 over x goes to minus infinity, so it's still similar to before. Now absolute value x is equal to minus x because x is negative, right? X goes to minus infinity this time, like minus 10, minus 100, minus 1000, and so on. So x is negative, so absolute value x is equal to minus x. So this will be limit as x goes to minus infinity, minus x times root 3 minus 1 over x divided by x times 4 plus 1 over x. Now x cancels with x, and I will have minus square root of 3 minus 0 divided by 4 plus 0. So the answer will be minus root 3 over 4. Minus root 3 . So it seems that this screen is freezed. Oh. Okay, here. So minus root 3 over 4 is the limit as x goes to minus infinity. So limit as x goes to infinity was root 3 over 4. Limit as x goes to minus infinity is minus root 3 over 4. So what are the horizontal asymptotes? It's the horizontal asymptotes are y equals root 3 over 4 and y equals minus root 3 over 4, right? So y equals root 3 over 4 because the limit as x goes to infinity is root 3 over 4, and y equals minus root 3 over 4 because the limit as x goes to minus infinity is minus root 3 over 4. So some people here say, for example, horizontal asymptotes are root 3 over 4 and minus root 3 over 4. That's not a correct answer because root 3 over 4 is just a number, right? So when you say horizontal asymptote, you have to specify a horizontal line, first of all, which is also an asymptote for your function. Horizontal line, the equation of a horizontal line is of the form y equals some constant. This is what you learned in high school, right? Y equals a constant is the equation of a horizontal line. So in this case, y equals root 3 over 4 and y equals minus root 3 over 4. These are two horizontal lines which are asymptotes for our function. Of this function here, if you want to know which one, because the question says that find horizontal asymptotes of this function. So I'm talking about horizontal asymptotes of, just to be more clear, I can also mention of root 3x squared minus x over 4x plus 1. So these are function and its horizontal asymptotes are these two horizontal lines. Okay, so now let's look at the next example. Find horizontal asymptotes of, let's say f of x equals square root of 3x squared plus x minus x. Horizontal asymptotes of this function. So to find the horizontal asymptote of function, we need to find the limit of that function as x goes to infinity and limit of that function as x goes to minus infinity. So we need to find limit f of x as x goes to infinity and limit f of x as x goes to minus infinity. So for the first one, limit f of x as x goes to infinity. So this will be limit square root of 3x squared plus x minus x goes to infinity. So how can we calculate this limit? So as x goes to infinity, the first term approaches what? So see this term here. So 3x squared plus x goes to infinity as x goes to infinity. You can easily verify this. Remember last time we did some examples similar to this, that we had a polynomial. Whenever you have a polynomial as x goes to infinity, the answer will be either infinity or minus infinity. Similarly, if x goes to minus infinity, again, the answer will be infinity or minus infinity, depending on the degree of that polynomial, whether it's odd or even, and also depending on the leading coefficient, whether it's positive or negative. In this case, you know, the degree is 2, which is even number, and the coefficient is 3, which is a positive. Leading coefficient is 3, which is positive. But we saw that you can easily calculate this. You just need to take highest power out, which is x squared, times 3 plus 1 over x. And then as x goes to infinity, this goes to 0. And then infinity times 3 will be infinity. So that's why I'm saying that the limit will be infinity as x goes to infinity. So you can write down this justification for this part. So the first part goes to infinity. The second part also obviously goes to infinity. So then the total final result here will be something of the form infinity minus infinity, because the first expression goes to infinity, second expression also goes to infinity, and then infinity minus infinity will be indeterminate. Remember, infinity minus infinity was one of the indeterminate forms here. I explained the reason last time. Infinity minus infinity means a very large number minus a very large number. Now it depends whether the first very large number, how big is it compared to the second very large number. If they are equally large, for example, 1,000 minus 1,000, the answer will be 0. But for example, 10,000 minus 1,000 will be 9,000, which is still very large, right? Or 10 million over 1,000 is still very large, right? So the answer potentially could be anything. That's why it's an indeterminate form. And when we have indeterminate form, we have to simplify. How can we simplify? We said to simplify when we have a square root involved, we can factorize, we can rationalize, right? So factorize to simplify, rationalize. So let's rationalize. Let's see what happens. So we have limit root 3x squared plus x, and then minus x as x goes to infinity. I'm going to divide and multiply by the conjugate of this. So what am I going to get? 3x squared plus x minus x times root 3x squared plus x divided by root 3x squared plus x as x goes to infinity. And then, so for the top, a minus b times a plus b is a squared minus b squared. So we'll have limit 3x squared plus x minus x squared divided by root 3x squared plus x goes to infinity. Now 3x squared minus x squared will be 2x squared. So again, the screen is freezed. Let's see whether the issue can be solved. And stop share. Share again. Yeah. So then this is limit 2x squared plus x divided by square root of 3x squared plus x plus x as x goes to infinity. Now we can factor highest power of x out from top and bottom. We will get limit x squared times 2 plus 1 over x divided by, in the bottom, the highest power of, inside the square root, highest power of x is x squared. So I can take x squared out, 3 plus 1 over x, and then plus x. Now this one I can write it as, so top is x squared times 2 plus 1 over x. Bottom, square root of x squared is absolute value x, which is equal to x in this case because x goes to infinity. So square root of x squared equals absolute value x equals x in this case. So x will come out. And if I take x out, which is the highest power of x, because this one, x will come out, right? After it comes out of the square root, x will come out. This is also x. So 1x here, 1x also here. I can take x out. And what will be left inside? It will be square root of 3 plus 1 over x plus 1, right? I'm taking x out because square root of x squared is x. When it comes out of square root, x comes out. Now that x, I'm taking it out. Then what will be left? Square root 3 plus 1 over x, and then plus 1. This x, if I factor x out, 1 will be left. X goes to infinity. Now I can simplify this power with this x. Now what will be left? It will be limit x, right, times 2 plus 1 over x divided by square root of 3 plus 1 over x plus 1. X goes to infinity. Now I can replace x to infinity. I will have infinity times 2 plus 1 over infinity is 0. Square root of 3 plus 0 means square root 3 plus 1. So it will be infinity times 2 over root 3 plus 1. Now infinity times a constant, positive constant in this case, is infinity. Infinity times a positive constant is infinity. Infinity times a negative constant is minus infinity. Right? Because infinity is a very large number, like 10 million, or 100 million, times a positive constant times 5, for example, will be 50 million or 500 million. So it's still very large positive. So the answer will be infinity. So the limit of this, so this is the final answer. The limit of this function as x goes to infinity is infinity. All right. Now let's calculate the limit of this function here as x goes to minus infinity. So far we have no horizontal asymptote, because horizontal asymptote happens if the limit as x goes to infinity is equal to a fixed number, fixed real number. Right now the limit as x goes to infinity is infinity, which is not a fixed real number. So far we have no horizontal asymptote, but let's also calculate the limit as x goes to minus infinity. Maybe we'll get a horizontal asymptote in that case. So for the other limit f of x as x goes to minus infinity is equal to limit square root of 3x squared plus x minus x as x goes to minus infinity. And then we'll have a limit. Okay, so this part, and it's a little bit tricky. Previously, remember when we're calculating the limit as x goes to infinity, we said we have two parts. One part, the first part goes to infinity, second part goes to infinity. Infinity minus infinity is indeterminate. But let's see what about this case. This case, the first term, because before deciding to simplifying or deciding to simplify or rationalize or factorize, first we need to figure out whether we have indeterminate form or determinate form. If we have a determinate form, for example, infinity plus infinity, then we don't need to simplify or rationalize or anything, because we know that infinity plus infinity is infinity, right? But if we have an indeterminate form, such as infinity over infinity or infinity minus infinity, then we have to simplify or rationalize depending on the type of function we have. But first, we have to know whether we have a determinate form or an indeterminate form. Now, let's look at the first term. What happens to the first term as x goes to infinity? So 3x as x goes to minus infinity, 3x squared plus x as x goes to minus infinity approaches infinity. Again, you can prove this similar to what I explained before, because we said that we can factorize x squared out, and then 3 plus 1 over x will be left. This will go to infinity as x goes to minus infinity, right? Because the first term will be like minus infinity squared times 3 plus 0. And this is infinity squared, which is infinity times 3 is infinity. So we can justify this way. And then minus x. So it will be, so the first part goes to infinity. What about x itself? We know that x itself goes to minus infinity. So this part, x goes to minus infinity. So what will be the result? The result will be the first part goes to infinity minus x. X itself goes to minus infinity. So infinity minus infinity. So this will be infinity plus infinity, which is infinity. That's it. We don't need to rationalize or simplify, because we have infinity minus infinity. Remember, infinity is a very large number, like 100 or 100,000 or 1 million or 10 million. So let's say 10 million minus of a large number. For example, 10 million minus 20 million. That means 10 million plus 20 million, which will be definitely, again, very large. So infinity minus infinity means infinity plus infinity. Infinity plus infinity is infinity. It's a determinate form, and therefore we do not need to simplify or rationalize. We will need to simplify or rationalize only when we have an indeterminate form. Okay, so this is the tricky part. In the exam, first make sure before doing any simplification or rationalizing, first figure out whether you have a determinate form or if you have an indeterminate form. Please have all the determinate forms in your mind and all the indeterminate forms in your mind, so that when you have infinity plus infinity, you immediately recognize that, okay, this is determinate, therefore the answer will be infinity. So I will add some indeterminate forms later during this course, but for now, just have the ones that I mentioned above in your mind about determinate forms and indeterminate forms. So anyways, the function, the limit of the function as x goes to infinity was infinity, and the limit of the function as x goes to minus infinity is also infinity. Therefore, we do not have any horizontal asymptote because neither of the limits are equal to any constant, because for having horizontal asymptote, limit of the function must be a constant, a fixed number, fixed real number, such as 5 or 10 or √2. If it's infinity, then we won't have any horizontal asymptote. So I can say that thus f of x has no horizontal asymptotes since both limits as x goes to infinity and as x goes to minus infinity are infinity. And another exercise you can think of later, find horizontal asymptotes of, let's say, f of x equals square root of 3x squared plus x minus √3 times x. So previously we had √3x squared plus x minus x is √3x squared plus x. Instead of minus x, we have minus √3 times x. So it's √3 times x. X is outside of square root. √3 times x. You will see that for this function, it's very similar, and the calculations will be also similar. But the limit at infinity this time will be a constant. And therefore, you will have a horizontal asymptote this time because the limit at infinity is a constant. The limit at minus infinity, you will see that still is infinity, but limit at infinity is a constant number, a fixed real number. Therefore, you will have a horizontal asymptote. So just a hint I wanted to give you, but please do the calculations and write down the details as a practice. All right. Okay, so now the next section, 1.6, continuity. So let's learn about the definition of a continuous function. So given a function f of x, intuitively, we say that f of x is a continuous function if the graph of f of x contains no breaks, and no holes. Okay, so just an intuitive definition of continuity, not the formal definition. So in the examples, always remember that when, for example, you're supposed to show a function is continuous, you cannot mention intuitive definition as your solution. So you can use intuitive definition or intuitive reasoning to get some idea, but it's not a formal proof for the exam. So if you use intuitive definition or solution, then you get maybe some points, maybe 1 or 2 points, let's say, out of 10 points, because it's just an informal reason, right? But if you want the full mark, you have to give the formal definition or solution for the question. I haven't mentioned the formal definition of continuity yet. So, but first let's learn about intuitive definition. So for example, let's say if you have a graph which has a hole like this. So this is a discontinuous function. So let's say if this is y equals f of x, because it has a hole, so this is discontinuous function. Or if you have if it has a break, let's say, for example, something like this, again, this is a discontinuous function. Okay, so this case or this case, the function will be discontinuous. But let's say if you have a function like this, so this is a continuous function. Okay, so now formally, a function y equals f of x is called continuous at x equals a if the following three conditions hold. So first of all, x equals a must be in domain of f, i.e. f of a is defined. Okay. So this is as opposed to the condition we had for the limit. For the limit of a function, when we talked about the concept of limit of a function at a point, we specifically mentioned that the point does not have to be in the domain of the function. But here for continuity, we require the point to be a part of domain of the function. So that's the first condition. And then the second condition is that limit f of x as x approaches to a exists. And the third condition is the limit f of x as x approaches to a must be equal to f of a. Okay, so when you look at this equality, limit f of x, x approaches to a equals f of a. But potentially for a function f, it's possible that the left-hand side does not exist, or it's possible that the right-hand side is undefined, right? So for some functions, f of a is undefined. For some function, limit f of x does not exist. But if you want to have continuity, this limit must exist, and this f of a must be defined. You cannot have something undefined. This has to be defined. This limit has to exist. And the value of this limit must be equal to the value of the function at the point. So if f of a exists and limit exists, and the values, the values of this f of a and this limit are equal, then we can say that the function is continuous at the point A. Okay, so let's look at an example. Let's say we have, for example, this function here, and or let's say this function, let's say this is 2, and let's say this is also 2, and let's say, for example, here we have a point, field point as 4. So, and let's say this is y equals f of x. So now the question is y equals f of x continuous at x equals 2? So this point is right above 2. Okay, so here. So we have to check if all these three conditions, all three of them hold, then we say that the function is continuous at the point. Otherwise, we say the function is discontinuous at that point. So let's check. First of all, x equals a must be in domain of f, meaning that f of a must be defined. So here f of 2, is it defined? So first condition, f of 2 is defined. And f of 2, the value of f of 2 is equal to 4, right? So f of 2 is defined as equal to 4. So that's the first condition. Then the second condition, the limit must exist. Does it exist? Limit f of x as x approaches to 2. So let's check. Limit f of x as x approaches to 2 from left. So if x is a little bit less than 2, so for example, around here, if x is around here, what can we say about the output? The output will be very close to 2, right? So as x gets closer and closer to 2 from left, output will be closer and closer to 2. So left limit is 2. And what about the right limit? Limit f of x as x approaches to 2 from right. So again, let's look at the graph. If x is a little bit more than 2, for example, around here or here, look at the outputs, they get closer and closer to 2 again. Outputs closer and closer to 2. So the right limit is also 2. So we can say that the whole limit exists because left limit and right limit, they both exist and are equal. So the whole limit also exists and the value is equal to the value of those limits, which is 2. The common value, which is 2, exists, and limit f of x as x approaches to 2 is equal to 2. So that was the second condition. And then the third condition, are they equal? So f of 2 and the limit, they both exist, but they are not equal because f of 2 is 4 and the limit is 2. So the third condition, f of 2 is not equal to the limit. Right? So that means f of x is discontinuous at x equals 2. So the first two conditions were okay, but the third condition does not hold. So that means the function is not continuous, or in other words, it's discontinuous at this point. So continuity or discontinuity, of course, depends on the function and also depends on the point. So at x equals 2 is discontinuous. But what about at another point? For example, let's say at x equals 0, for example. Let's say, for example, this point here, this value here, let's say 1.8 or 1.6. So this is 1. Oh, sorry. Let's say this is 1.6. So let me add part B. Is f of x discontinuous at x equals 0? Or let's say is f of x continuous at x equals 0? So this time the answer is yes. So see, at x equals 2, the function was discontinuous because the value of the limit and f of 2 were different. But at x equals 0, the value of the limit and f of 0 are the same. How can we see? So see, at x equals 0, we can say that f of 0, so the first condition, f of 0 is equal to, how much is it? F of 0, the value of the function at 0, the output is 1.6. So f of 0 equals 1.6. Second condition, left limit and right limit. They're also both 1.6, which means the whole limit exists and is equal to 1.6, right? So if x is a little bit less than 0 or a little bit more than 0, then the output will be very close to 1.6. So the limit will exist and is equal to 1.6. And the value of the limit and the value of the function at the point, they're equal to each other. So the third condition, f of 0 equals limit f of x approaches to 0, and this is equal to, they're both equal to 1.6. Thus, f of x is continuous at x equals 0. Similarly, check that f of x, that y equals f of x with the graph above, with the graph shown above. Is continuous at x equals c if c is any real number except 2. So only at 2 the function is discontinuous because the value of limit and f of the number were different. But at 0 or at 1 or at 3 or at 10, at any c other than 2, let's say if c is 0 or if c is 1 or if c is 3, any c other than 0, the function is continuous. Only at 2 is discontinuous. Okay.